Dear student, uh, today in this class we will discuss some parts of the chapter Cauchy solution of differential equation special function for this chapter, and already we studied in last four chapters some plus four classes in some part of this chapter, and in this chapter we mainly focus on the Hermite differential equation. And here is the outlines here to cover the topics which will be covered in this class. These are Hermite differential equation, its solution, and then Hermite find out the values of Hermite polynomials h and x, which is denoted as h and x, and then the genetic function for h and x, that is for Hermite polynomials, and then Rodrigues formula for Hermite polynomials, and finally some Hermite polynomials, calculation of some Hermite polynomials using Rodrigues formula. So come to the first topic, that is Hermite differential equation. The Hermite polynomial, the Hermite differential equation is given here. It has the form as d2y by dx square minus 2x dy by dx plus 2ny, that is equal to 0. And here n is the non-negative constant, and this equation is the Hermite differential equation, and this can be solved by power series method. But before to do this, we have to check whether this equation can be solved by power series method or not. And all of them, the importance of Hermite polynomial, Hermite differential equation should be stated once. And in case of in case to determine the eigenstates of the quantum harmonic oscillator in systems theory in connection with nonlinear operations, the Hermite polynomials are widely used, routinely used. So in case of quantum harmonic oscillator, to determine the eigenstates, Hermite polynomials is routinely used. And there are different broad spectrum of in physics in which Hermite differential equation are usually used. So first, and now come to or check whether this equation can be solved in power series method. To do this, we have to check its singularity, and just compare this equation with the general form of the linear homogeneous differential equation, which is p0 d2y by dx square minus plus p1 dy by dx plus p2y, that is equal to 0. You will have p0x, that is equal to 1. So p0 is equal to constant in this case. If you use the value of x as 0, then p0 is equal to 1, that is constant. That means it is not equal to 0. So x is equal to 0 is an ordinary point of Hermite differential equation. So around x is equal to 0, the power series solution of Hermite differential equation can be possible, and since it is possible to expand Hermite polynomials, Hermite differential equation in power series method, so you can write y is equal to r is equal to 0 to infinity a r x to the power m plus r. That means in this case x is written in ascending power of x. So the solution is ascending power of x. So from here dy by dx is calculated. Dy by dx is equal to r is equal to 0 to infinity m plus r a r x to the power m plus r minus 1. Now d2y by dx square is equal to r is equal to 0 to infinity. Just differentiate this. You will have m plus 1 first, and then m plus r minus 1. A r x to the power m plus r minus 2 will be here. M plus r minus 2. So now substitute these values, that means the value of y dy by dx and d2y by dx square in the familiar Hermite differential equation, that is in this equation. So what it will be, we will see that r is equal to 0 to infinity The first term is m plus r into m plus r minus 1 x to the power m plus r minus 2, since it was the 2y by dx square. Then minus 2x was there, so minus 2 into m plus r into x to the power m plus r minus 1 plus 1. That means it will give you minus 2 into m plus r x to the power m plus r, and the last term was a 2n into y, that is 2n x to the power m plus r, and ar is here. So this will give you just simplify the last two terms. The first term is written as usual, minus 2 into m plus r minus n into x to the power m plus r, ar, that is equal to 0. So equation 3 actually is an identity equation, and which actually has every value of r. So equation 3 is an identity holding every value of r, and so the coefficient of the different power of x must be 0. And now equating the lowest power of x, that is in this relation the lowest power of x can be obtained by using r is equal to 0. If you use r is equal to 0, then it will give you m minus 2. So the lowest power is m minus 2. And now equating the coefficient of the lowest of x, that is x to the power m minus 2 to 0, we have from the first term here r is equal to 0, say m into m minus 1. This term will give you m into m minus 1 into a0 from here. A0 from here, you will get nothing from this term, that is equal to 0. And from here you can easily write m into m minus 1, that is equal to 0, because a0 cannot be 0 because it is the first term of the series, and the first term of the series can never be 0. That's in this sense you can write m into m minus 1 is equal to 0, or m is equal to 0 from here, m is equal to 0, or m is equal to 1. So you have two values of m, one is 0 and another is 1. Now again computing the equating the coefficient of x to the power m minus 1. So to obtain the coefficient of x to the power m minus 1, you have to replace r by 1. So here m minus 1, if you wish to compare the coefficients of x to the power m minus 1 from both sides, you have to replace x to the power m minus 1. The second term is x to the power m minus 1, so you have to replace r by 1. So if you replace r by 1, so this will give you m plus r minus 2, that is m minus 1. And then from this term you will have m plus 1, since r is equal to 1, and from this m. So m into m plus 1, that will into from here a1. So you have here m into m plus 1 into a1, that is equal to 0. I write it as equation 5, and this is equation 4. And if these two equations have to be satisfied with the values of m or a1, then either m should be 0 or a1 should be 0 or both should be 0. That means if m is equal to 0 or a1 is equal to 0 or both 0, then these two equations will satisfy simultaneously. So from here we have a1 is equal to 0 or m is equal to 0 or both is equal to 0. That is for a1 is equal to 0 and m is equal to 0. This is the condition. So now equating the coefficients of the general term x to the power m plus r. To obtain the general term x to the power m plus r, here is x to the power m plus r, this is okay. And from here, if you have to compare the coefficients of the general term m x to the power m plus r from both sides, then you have to replace r by r plus 4 in this for the first term. So you have to replace from the first term. What you will have x to the power m plus r, no, x to the m plus r, you have to replace r by r plus 2. If you replace r by r plus 2, so m plus r plus 2 minus 2 will vanish. So from here you will have x to the m plus r. So r should be replaced by 2. So from here you have m plus 2, and from here m plus 1. So m plus 1 into m plus 2 into from here a r plus 2. So the first term will give you m plus r plus 2 into m plus r plus 1 into a r plus 2, and then from the second term, that is from this 2 into m plus r minus n into a0 is here. No, ar is here, from ar is here. So this will give you minus 2 into m plus r minus n, ar that is equal to 0, and from here a into r plus a r plus 2 that is equal to 2 into m plus r minus n by m plus r plus 1 m plus r plus 2, and which gives the recurrence relation between the coefficient, and I write it as equation 6. Now, since we have two permissible values of m, one is m is equal to 0 and another is m is equal to 1, so there are two cases which are to be studied. Number one is when m is equal to 0. When m is equal to 0, then from equation 6, m is from equation 6, we will have a r plus 2 that is equal to 2 into r minus n by r plus 1 into r plus 2 into ar. This is written here. So this is equal to 2 into r minus n, r plus 1, r plus 2 into ar. Now for r is equal to 2, you will have a2 that is equal to minus r is equal to 0 here, so minus 2n by 1 from here 1, and 2 1 into 2 a0 that is equal to minus 2n by 2 factorial into a0, and then a3, that means in this case r is equal to 1. So if you use r is equal to 1 in this relation, then a3 will be 2 into from 2 into r is 1 minus n by 2 from here and 3 from here, so 2 into 1 minus n by 2 into 3 into a factorial. A1 is equal to 0, that is equal to 0 because a1 is 0, which was found previously. So similarly, a5, a7, etc., the word all odd terms of a will vanish. So there will be only the even terms of a. Now for a4, so in this case r is replaced by 2 in this relation. R is, if we replace r by 2, then ar plus 4. Ar plus 4 is there, and then it will is equal to 2 into 2 minus n by 3 into 4 from here into a2. Just substitute the value of a2 in this relation, that is minus 2. It is written, this minus 2 is this minus 2 is here, and then 2 minus n and 2n. The a4 is 2 into 2n minus n into 3 this and a2. Just use the value of a2 here. You will have the minus sign is taken first, and then 2 into 2 minus n, and this 2n is there, and 2 factorial 3 into 4 into a0, that is equal to 2 square. You can write it as 2 square this 2 and this 2 square a minus 2 by 4 factorial a0, and so on. So in this way the last term will be, if you write the last term as 2k, then that means k is equal to here. Just compare, just see this relation. Here if you consider this is just 2k, so k is equal to 2. So first is 2 to the 2 square, that it can also be written as minus 2 square. That means it will give you minus 2 to the power k if you compare just with this. So k is equal to here, so this can be written as minus 2 to the power k. What is written here? And then n into n minus 2. In this way, the last term here, in this case, you have n is equal to 2, so the last term is n minus 2. That means it can be founded by 2k plus 2. So if you use k as 2 for case of these, so it will give 2 into 2, that means minus n minus 4 plus 2, that will give you n minus 2. So it is okay, it is correct. So the last term in this case will be n minus 2k plus 2 by here 4 factorial. That means in this case you use as k is equal to 2, so it is equal to k factorial. So the final term is this. So the solution, general solution, now the general solution is y is equal to r is equal to infinity ar x to the power m plus r. That is equal to, in the first case we have taken m is equal to 0. So r is equal to 0 to infinity ar x to the power n, that is equal to a0 a1x a2x square a3x2 plus a4x4 and all other terms. But this term a1 a3 a5, that is the odd terms of a as they are 0. So you can write y is equal to a0, a2x squared plus a4x4 plus all other terms. So now substituting the values of a0, a2, a4 in this relation, you will have y is equal to a0 first term 1, the second term, that means for a2 it was minus 2n by 2 factorial into x squared. See here they all of them are calculated here it is here, and then the next term will be minus 2, and then the next term will be minus 2 whole square or 2 square into n into n minus 2 by 4 factorial into x to the power 4, and in this way the last term is as given here, the last term will be minus 2 to the power k n into n minus 2, in this way n minus 2k plus 2 by 2k factorial into x to the 2k. So just this is written once again here, and it is for a1 is equal to 0. This is I numbered this equation as 7. So if however a1 not is equal to 0, if in this case the 1 was taken as 0, but if a1 is not is equal to 0, then a3 a5 all the odd terms of it will not vanish, and since it was calculated, it can be calculated, that is a3 can be calculated using this relation, using this relation. So then also actually you have already calculated a3 is equal to 2 into 1 minus n by 2 into 3 into a1, okay, into a1. That is also calculated or written here. This is equal to this, and now a5 can be calculated in the similar manner, and this is the whole calculation is given here, the whole steps, and finally we'll have s2 square n minus 1 n minus 3 by 5 factorial into a1. So in this way the last term or general term, it is better to say the general term can be written as, if you use just 2k plus 1, so in this case k is equal to 2 here, just compare this to 2k plus 1, so k is 2 here, so you see here minus 2 to the power 2 square, so k is 2 here, so it is written as minus 2 to the power k, then n minus 1 n minus 3. In this way the last term is n minus 2k plus 1. Just compare this with this. In this case k is equal to 2, so last term is 2k, that means 4 plus 1, that means minus 3, so it is okay, fine. So the general term can be written as 2k plus 1 is equal to minus 2 to the power k n minus 1 n minus 3. In this way the last term is n minus 2k plus 1 by 2k plus 1 factorial into a1. So the general solution is nothing but the combination of the term that is given in this equation, that is 7, that means this entire term plus the term that will come due to the presence of a1, that means the second term will be a1 into for the first term a1 into x, because x is there with a1, so for the second term will be e1 into x, then minus then the term will come a3, then minus 2 into n minus 1 by 3 factorial into x cube, and then plus 2 square n into n minus 2 by 4 factorial into 2 square into n minus 1 into n minus 3 by 5 factorial, and first term is this and second term is 2 into n minus 1 by 3 factorial into x cube, and then 2 square into n minus 1 n minus 3 by 5 factorial into x to the power 5. In this way the last term is from here, just write this. So this x to the 2k plus 1. This is written as equation 8. So this is the complete solution when a1 not is equal to 0. However, if a1 is equal to 0, then only the first term, this first term will present here. However, it is written here also, and in this case the first term will exist there when a1 is equal to 0, and then y is equal to this, and write it as y is equal to u. Just say it. However, if m is equal to 1, then from this relation, if m is equal to 1, then from this relation ar plus 2 is equal to 2 into 1 plus r minus n by r plus 2 into r plus 3 into ar, and I write here this, I write this here in this relation, where it is here. When m is equal to 1, ar plus 2 is equal to 2 into r plus 1 minus 2n by r plus 2 into r plus 3 ar. Now putting 1, r is equal to 1, 3, 5, etc. As it was done in the first case, or that is for m is equal to 0, as you saw that a3, a5, etc. is 0. So in this case also a3, a5, all terms of a will vanish. So just use 0, r is equal to 0 or even terms. So if you use r is equal to 0, then a2 from this relation, a2 is equal to 2 into 1, that means 2 minus 2n by 2 from here and 3 from here into a0, that is equal to minus 2 into, it can be written as minus 2 into n minus 1 by 3 factorial into a0. Similarly, a4 for r is equal to 2, a4 is equal to 2 into 3 from here minus 2n by 4 from here and 4 from here and 4 from this r plus 2 and 5 from here. So that into a2, that is equal to 6 from here, 6 minus 2n by 4 into 5, and here substitute the value of a2, that is this 2 into n minus 1 by 3 factorial into a0. And after doing simplification, this will give you, if you use minus 2 as common term from here, then it will give you n minus 3, and minus 2 from here and minus 2 is there, so it will give you 2 square, or in generally minus 2 to 2 whole square. Then n minus 1, n minus 3 by 5 factorial, it can be written as 3 factorial 5 into 4 into 3 factorial, that means 5 factorial into a0. So in this way, the general term can be written as a 2k, that is equal to minus 2 to the power k, n minus 1, n minus 3. In this way, the last term is n minus 2k plus 1 by 2k plus 1 factorial into a0. Just substitute the different values of k, you will have a0, a2, a4, a2, a0. You can check in this case, and all other even terms can be calculated using this relation. So here, so the general solution will be for m is equal to 1 in this case, y is equal to r is equal to 0 to ar x to the power r plus 1. So that will give you, from for r is equal to 0, it will give you a0x, then r is equal to 1, a1 x square. In this way, a2 x2, a3 x4, a4 x5, and in this case the last term will be a2k x to the power 2k plus 1. And since the odd terms of a does not exist, so for due to the vanishing of a1, so this y can be written as a0 ax, a2 x2, a4 x5. In this way, a2k x to the power 2k plus 1. Now let's substitute the values of a2 f and a2k from that was calculated earlier. So just substitute this. You are here the values of a2, a4, a2k are calculated. Now just substitute these values, and you will have x a0 into x minus 2 into n minus 1 by 3 factorial x cube plus, you can write it as minus 2 to the power 2 or whole 2 minus 2 whole square into n minus 1. You can write this as, or left it as 2 square, n minus 1, n minus 3 by 5 factorial x5 plus the last term is minus 2 to the power k, n minus 1, n minus 3. In this way, n minus 2k plus 1 by 2k plus 1 factorial into x to the 2k plus 1, and you will hit it as v. Now y is equal to v, just hit it as v. Now just you go to equation, you see that this term x minus this term is also present in equation 8. 8 is here, is also present in this equation. Just this term, say that for the first case, when a1 not is equal to but m is equal to 0, a1 not is equal to 0 but m is equal to 0, solution was this. And the second term within the bracketed term, this is equal to this is nothing but the solution, the second solution, that is for m is equal to 1, that is this. It is easily it can be easily seen. So here you should note that the equation 10, that is this equation, is a part of equation 8. As you see, as I not as I indicated. Okay, so it's a part of equation 8, but both being the solutions of the same differential equation. So therefore, equation 10 cannot be a part of solution given by equation 8. So you see that these this part, that is this part this part is included in case of m is equal to 0 but a not equal to 0. That means equation 8. In equation 8, you see here equation 8 is there. Equation 8 is there. So actually, what we obtained in equation 10, that is within this. But since these are the solution of same differential equation, so in equation 8, this term cannot be there in this equation 8, as these are two independent solutions. So the solution as given in equation 10 cannot be here. So only the term that will be in this case, that is for m is equal to 0, is y is equal to this first term. So this is taken as u, and in equation 10, the solution given in equation 10 is given as b, and these two are two independent solutions. And then you have that a1 should be 0, and the general solution will be the linear combination of the solution given by equation 8 except the last term, the second term, and equation 10. So then you will have y is equal to au plus bv, where a and b are two arbitrary constants. Now go to Hermite polynomials, and as you know that the solution, any solution of Hermite differential equation is called the Hermite polynomials. So, and it is noted by Hn for the order of n. So, and if you use the constant a0 as just 1 to the power n by 2 into n factorial by n by 2 factorial, then you can easily find out different values of the Hermite polynomials. And now recalling equation 9, that is the solution of Hermite differential equation as it is given in equation 9, that is y is equal to a0 into this 2n by 2 factorial x square plus 2 square into n minus 2 by 2 factorial x to the power 4, and in this way the last term is this. Then the coefficient of x to the power n. Now if you wish to find out the coefficient of x to the power n, you have to replace here in the last term here 2k as n. Okay, if you use 2k as n, then k will give you n by 2, and then from on the last term you will have a0 first. So a0 is given by minus 1 to the n by 2, as you have considered it as here, and then n factorial by n by 2 factorial into, you see here k is equal to n by 2, so here minus 2 to the power n by 2, and then into n minus 2. In this way n minus 2k is equal to n here, so n minus n, and then plus 2. So that is by 2k is n, so n factorial is here. So these n factorial will cancel each other, and from here you can separate another term minus 1 to the power n by 2 into, then 2 to the power n by 2 will be there. So this minus 1 to the power n by 2 and this minus n to the power n by 2 will give you minus 1 to the power n, and then 2 to the power n by 2, and all other terms can be written as, the last term is here 2, so it can be written as 2 into, this can be written n by 2, and this term can be written as 2 into n by 2 minus 1, and in this way the last term 2 can be written as 2 into 1 by n by 2 factorial. So in this way, in this series, what you are observing, that is 1 into 2, in this way 2 is multiplying with all other terms up to n by 2 terms. So there are n by 2, there are multiplication of n to n by 2 times in this series. So you can write it as 2 from here, 2 from all other terms, and 2 from n by 2 terms. It will give 2 to the power n by 2, and another 2 to the power n by 2 was previously. So 2 to the power n by 2, and from this series another 2 to the power n by 2, and then the rest of the series are n by 2 into n by 2 minus 1 in this way the last term is 1. Okay, by n by 2 factorial, that will give you from this to the power n, and from this is nothing but n by 2 factorial, and this is n by 2 factorial, that is 2 to the power n. So the coefficient of x to the power n is 2 to the power n. Now if you wish to find out the coefficient of x to the power n minus 2, and it can be obtained by taking 2k is equal to n minus 2, or k is equal to n minus 2 by 2, then from the last term, that is from this term, first you substitute the value of a0, that is a0 is equal to minus 1 to the n by 2 n factorial, n by 2 factorial, then minus 2 to the power k was there, so you substitute the value of k, that is minus 2 to the power n minus 2 by 2, then n into n minus 2. In this way, n minus 2k plus 2 was there, so n minus, just substitute the value of 2k minus n, another minus will give you plus 2, and the last term is plus 2. That is just you use 2k is equal to n minus 2, so that will give you n minus n, then plus 2, and then plus 2. So this will give you, and in the denominator it was 2k factorial, so that is n minus 2k factorial. So it will give you from here minus 1 to the power n by 2 is here, and from here minus 1 to the power n minus 2 by 2 can be extracted from this term. So that will give you minus 1 to the power n by 2 plus n minus 2 2. Okay, and then the left term here is plus 2 to the power n minus 2 by 2. Okay, and this n factorial can be written as n into n minus 2, and then n minus 2 factorial. Okay, it can proceed up to n minus 2 factorial, and this denominator is here n minus 2 factorial, and then from here and this is n into n minus 2. In this way, the last term is 2 plus 2, that is 4, that can be written as 2 square. So these will cancel each other, so you can write minus 1 to the power n minus 2, then 2 to the power n minus 2 by 2, and then n into n minus 1, n into n minus 1, n into n minus 1 from this, and then n into n minus 2 from here, and in this way it goes up to 2 square. Okay, so you can now write it as look at here, this is minus as n is even. Okay, so this will give you a negative sign. So negative sign is there, and then 2 to the power n minus 2 by 2, or you can left it as minus 1 to the power n minus 1. Then this term is written here n into n minus 1, and from this term you can write 2 into n by 2, n by 2 minus 1 into 2, in this similar fashion as that it was calculating the first case. And the last term in this series is 2 into 2. I write here another term 2 into 1. So in the denominator 2 into 1 should be there in the denominator. And here you can write this n by 2 factorial, and from here 1 factorial in this fashion. So this will give you minus 2 to the power, or you can left it as minus 1 to the n minus 1. Okay, then 2 to the power n minus 2 by 2, n into n minus 1, then 2. You see here that n is multiplied how much time? It is n by 2 times from this time. That means here 2 from here, and in this way, actually if this term was calculated, then it would be n by 2, but here the term, okay, the term is 2 into 1, and the last term is 2 into 2 to the 0 into 1, the last term was 2 to the 0 into 1. So you, and from each term, since 2 is coming out, so you can write as 2 to the power n by 2 minus 1, since the last term is not present here. So from here you can write 2 to the power n by 2 minus 2. Okay, now then from all other terms, that is 1 into 2 into 3 into this in this way, n by 2 factorial is also there, and from here n by 2 factorial into 1 factorial. Okay. Now because one thing is there from this series. Okay, from this series 1 into 2 into 3 in this way, last term is n by 2. Actually this way, so up to n by 2. So these in all, if you extract 2 from all these terms, so it will give 2 to the power n by 2 actually. And due to this term 2 in the denominator, so total power of n will be 2 to the power n by 2 minus 1. 2 minus 1. So it will be 2 to the power n minus 2 by 2. And all this term will give you n by 2 factorial, and this is denominator. So approximately you will have minus 2 to the power n minus 2, n into n minus 1 by 1 factorial. So the coefficient of x to the power n minus 2 is minus 2 to the power n minus 2 into n into n minus 1 by 1 factorial. Similarly, the coefficient of x to the power n minus 4 is given in accordance with this, that is equal to since the first term was minus 1 to the power n minus 1, so it is negative. But for the second, for case of n minus 4, it will be minus 1 to the power n minus 2 will be there. Here minus 1 to the n minus 2 will be there, that is it will be a positive sign. So 2 to the power n minus 4, then n into n minus 1, n minus 2. In this way, see, you see that it is for x to the power, this was for x to the power n minus 2. So this is this goes up to n minus 1. So it will goes up to n minus 3. Just think of, just compare, you will understand. And then 1, instead 1, it will be 2 factorial. So thus yn will give you 2 to the power, just substitute the values, and then you will get yn is equal to 2x to the power n minus n into n minus 1 by 1 factorial into 2x to the n minus 2, then plus n into n minus 1, n minus 2, n minus 3 by 2 factorial into 2x to the power n minus 4. And just substitute the values of different coefficients of x, and final term will be this minus 1 to the n by 2, n factorial by n by 2 factorial, that is the reciprocal stuff. Okay, so you can write it as, since it is nothing but hnx, that is the Hermite polynomial, that is yn is equal to hnx, and I write it as this. So hns is the hn is called the Hermite polynomial of the approximation. So if now generally hn can be written as r is equal to 0 to n by 2 minus 1 to r n factorial by r factorial into n minus 2r factorial to 2x to the power n minus 2r when n is given, and if n is odd, then you can write hn as according as written here in this way. And if you use different values of r or substitute r in these two relations, you can find out all the coefficients of x as calculated here, as calculated in this calculation and its previous calculation. So you can check it, or you can take it as your homework to compare from this relation. Okay, now we are coming to the generating function for Hermite polynomials. As in case of Legendre polynomials, the Hermite polynomials can be generated from some functions which are called the generating function. In case of Hermite polynomial, the generating function is given by e to the power 2xt minus t square, that is equal to n to infinity t to the power n by n factorial hnx, that is given as equation 1, as in the same fashion that was taken in case of Legendre polynomials, but the generating function is different from that. So to prove it, we first expand this term here. So e to the 2xt minus t square can be written as e to the 2xt into e to the minus t square. Now if we expand the series e to the 2xt or e to the minus t square in series, then if we have r is equal to 0 to infinity 2xt to the power r by r. So just use different values of r and expand this, you will have the same values. So this can be written as this, and then e to the minus t square can be written as s is equal to 0 to infinity minus t t square to the power s by s factorial. It is taken as another integer. No problem is there. Okay. So then r is equal to 0 to infinity, rs is equal to 0 to infinity minus 1 to the power s from this term minus 1 to the power s is there, and from here 2x to the power r and factorial s r is here and factorial s is there, and the power of t in this case is t to the power r, and from here minus 2x. So t to the power plus 2s is there as minus 1 is taken here. So t to the power r plus 2s. So finally we get e to the power 2xt minus t square is equal to r is equal to 0 to infinity, r is equal to 0 to infinity, s is equal to 0 to infinity minus 1 to the power s, 2x to the power r factorial, s factorial, t to the power r plus 2s. So the coefficient of t to the power n for fixed values of s. So in this case the coefficient of t to the power n for fixed values of s for certain definite values of s, just here, right here, the coefficient of t to the power n. To do this, you have to replace r plus 2s as n. So such that this will give you t to the power n, and then the coefficient here will be minus 1 to the power s, 2 to the power x, 2x to the power, since r is replaced by this. So from here r is equal to minus 2s. So you have to write it as 2x to the power n minus 2s, and then r is equal to n minus 2s factorial, and then s factorial. And total coefficients of t to the power n can be calculated by summing over all this term, and for allowed values of s. And the allowed values of what would be the allowed values of s? Since r is equal to 0 to infinity, so r is greater than is equal to 0. So n minus 2 should be greater than is equal to 0. What is written here? And from here you can write s is less than equal to n by 2. So for even n starts from 0 and ends at n by 2. And for case of odd values of s will starts from 0 and it will ends at n minus 1 by 2. This is written here. So the required coefficient of t to the power n is just sum over all the terms, s is equal to 0 to n by 2. This is for even s, minus s to the power even n is to the power minus 1 to the power s, 2x to the power n minus, just substitute the values by n minus 2s factorial, s factorial, and this is just see here the Hermite polynomial was given by hnx, that is equal to r is equal to 0 to infinity minus 1 to the power r factorial. Here is n factorial into n minus 2r factorial, 2x to the power n minus 2r factorial. Just multiply this equation in the numerator by n factorial and in the denominator by n factorial. So this will give minus 1 to the power s, 2x to the power n minus 2s into n factorial by 2n minus 2s factorial, s factorial, and here 1 by n factorial. And first term will give you the Hermite polynomials, that is hnx, and n factorial is there. So finally you get e to the power 2xt minus t square is equal to n is equal to 0 to infinity n hnx by n factorial. This is the coefficient of t to the power n, and here t to the power n. So I write it once again. It is equation 2, and this is the form of generating function. And from this, the left hand side can be write in different fashion. Write it as e to the power x square minus x square plus 2xt minus t square. That is equal to n is equal to 0. That's the line. Just write it. Write the right hand side here. So this is written, can be written as e to the power x square minus x minus t whole square, and this is written here. This is equal to this. So this is equal to then e to the power, and this can also be written as e to the power x square minus t minus x whole square, that is equal to n is equal to 0 to infinity t to the power n factorial is n h. So equation 2, 3, 4 are the different forms of the genetic function of Hermite polynomials h and x. Now Rodriguez formula. So one of the generating function, as we have calculated in the previous section, that is e to the power x square, e to the x square minus t minus x whole square, that is equal to this. I used here this relation. So this is written here, n is equal to 0 to infinity t to the power n by n factorial h n x, that is equal to e to the power x square minus t minus x whole square. That can be written as e to the power x square into e to the power minus t minus of t minus x whole square. This is equation. In this section, I write it as equation 1. Now differentiating this equation with respect to n times. that means I have to differentiate this equation to n times with respect to t. From first term, you will get if you forget, this is the sum over n is the first term for n is equal to n is equal to um, first first type first first order differentiation. So you will have n into t to the power n minus 1 and all other terms are there. And then for the second differentiation, you will have the n into n minus 1 and t to the power n minus 2 and all this stuff. In this way, if you differentiate n times, the final term will be 1. And then you will get n into n minus 1, n minus 2. In this way, the last term is 1. By this n factorial is there and hn is x is there. And from here e to the power x square, since you are differentiating to n times, and so dn by dtn e to the power t minus x whole square. So then from here it is n factorial by n factorial is there, hn x is equal to e to the x square, dn by dtn e to the power t minus x whole square. So now just put t is equal to 0 in this relation. So you will have hn x is equal to e to the x square dn dtn e to the power t minus x whole square at t is equal to 0. So now substitute or let u is equal to t minus x, and from here t is equal to since for at t is equal to 0, u is equal to minus x or x is equal to minus u. So here you can write is as t is equal to 0, so del t that should be equivalent to del u, because it is written here u is equal to t minus x, so u plus x is equal to t, or x is equal to minus u, so u minus 2 is equal to t, or that means t is equal to 0. One can write del u of a function or a constant that will be since t is equal to 0, so and u is also 0 from here. No. So then you can write del u of c that is equal to del t of c, and that both c is a constant and both will give you 0. So from there del u is equivalent to del t. That is written here. So from the right hand side will give you the second term of right hand side del n del t n e to the t minus x whole square t at t equal to 0, that is equal to del n del u n e to the power minus x square. Since it is t is equal to 0 here, so it will give you minus u square. That is because e to the power this will give you t is equal to 0, so e to the power x square, and x is equal to minus of u. So this will give you e to the minus x square minus u square, that is equal to minus 1 to the power n, or no, this will give you t minus x is equal to u. So it will give you del n del u n e to the power minus x square. So all this term here, there will be a negative sign, here will be a negative sign. So just modify it in your practice. This is minus negative sign. So here also, here this will be negative sign. So in this way it will be minus u square, and that can be written as since u is equal to minus x, so if you differentiate n times, so there will be another extra term minus 1 to the power n, then del xn e to the power minus x square. So finally you obtained minus 1 to the power n del xn e to the power minus x square. So hn x is equal to minus 1 to the power n e to the power x square from here, and the rest term is e to the power dtn of e to the power minus x square, which is the differential form of the Hermite polynomials and is called the Rotix formula. Now substituting different values of n is equal to 0, 1, 2, 3, etc. in equation 2, that means in this equation you will get different values of Hermite polynomials. For first case n is equal to 0, just use n is equal to 0 in this relation and calculate accordingly. You will get h0 x is equal to 1. The entire calculation is given here, and in this way h1 x is equal to finally we get h1 x is equal to 2x. just calculate, and all the calculations are given here, and h2x is go through all these calculations, and this is very simple calculation, and all the steps are done here, and finally we will get h2x is equal to 4x minus 2, and in similar fashion h3 will give you this, and this is the total whole calculation, and just to practice, and you will finally get either this 3x is equal to 8x cubed minus 12x. So in this way all other Hermite polynomials can be calculated, and you have to what to do, you have to just use n is equal to 1 to 3 etc. to this equation, Rodriguez formula, to this Rodriguez formula, and you will obtain, you will get, and you will get then all the Hermite polynomials. But you have to practice, first to practice up to 3 or 4 terms, that is the 3 or 4 Hermite polynomials. And this is the end of this lecture, and obviously you have to practice more and more, and then all the things will be